Okay, so I believe now we got some understanding actually what is surface tension. And if you see here, this is the perfect example, this to animation. You can see this water drop on the water surface. You can see how it's changed the water. This is actually the surface tension. And you see here the insects, they can easily walk on the water surface, but as a human being, we can't walk on the water surface. This is because of the surface tension. Anyway, so if you're interested, if you actually want to know more, I will definitely tell you can go through the books, because I actually want to make this video as short as possible. Otherwise, yeah, it will be difficult for you to follow these videos. Anyways, so let's go here. So we already explained what is surface tension, and this is only possible in liquids, not in solid. This is a force per unit length. So this is the formula you can see, and it found only at the interface, that means the water interface. There is some, you see this example here. So if we say, okay, this is actually the interface. Anyways, so I will escape this surface tension. Actually, I don't want to tell more about this. I believe that I actually wanted to give you some sort of understanding what is surface tension, and I believe now you got some understanding. So for better understanding, yeah, just please read the books. The other thing is the vapor pressure. Last time I explained what is vapor pressure. Today we're going to solve one question, so I put this one here again. So the vapor pressure of a liquid is the equilibrium pressure of a vapor above its liquid. That is the pressure of the vapor resulting from evaporation of a liquid. So last time I explained, actually you have a water pot, and it is filled with water. Maybe half, it is half filled with water. If you put some heat on the bottom of the surface, then it will start evaporating at 100 degrees centigrade temperature. So that vapor, it will just try to escape. So it will come up and it will try to escape. But when it is the water pot is completely sealed, so it can't go up. It can't just escape. So what will happen eventually is just it will go down, and it will create some sort of pressure on the water surface. So that was the vapor pressure. I believe that you already know what is vapor pressure, because last time I draw some the figure, and I explained actually what is vapor pressure. So I believe that you have some understanding, and today I think the way I explain vapor pressure, it is not enough, but I believe you know what is vapor pressure. So in simply we can say vapor pressure is a pressure which is created by the vapor on the water surface. So now the other thing is the bulk modulus of elasticity. We can say we can define this is as E. So let's say this is a elastic rod, and the length is L. So this is elastic rod, and length is L. If we put some sort of weight, look, this is the weight W. If we put some sort of weight here due to the gravity, you see it is an elastic rod. So when you are just applying some sort of weight here, it will extend. Let's say this extension or the increase is delta L. So delta, we usually use this term Greek symbol delta to express the rate of change. So delta L, this is actually the change. Now for a string or a rod, stress is actually how much force you are applying and what is the area. So it is force over area, that's actually the stress. And what is the change of the length? You see initially it was L, and now the change is delta L. So this is actually the relative change. So this is delta L over L is the relative change of length. So from the formula, the bulk modulus of elasticity, this is actually equal to the Young's modulus, and it is Young's modulus is stress over the relative change of the length. So that means E equals, so we said the bulk modulus of elasticity is E, so E equals stress over the relative change of length, which is delta L over L. This is for an elastic rod. Now, if we consider this bulk modulus of elasticity for water, let's say water. So for water or any fluid, consider in a state of the length, so water has volume, not length. So consider a container with an initial volume V, and so if we apply some sort of extra force F on the area A, so you can remember force over area, this is actually pressure. So that means if we apply some sort of force on a certain area, then we will get the pressure, right? So that means it will be pressure in a state of stress, and the relative change of the length. So if it is fluid doesn't have the length, it has volume, so that should be the relative change of volume. That means in a state of delta L, it should be delta V. So you see the pressure causes volume to decrease by delta V. We will solve one problem today, definitely. So this is all the questions we have, and now we will start solving the problems. Alright, so we already discussed some theories initially actually that we need to solve today's problem. So you can see this is actually the second question, and if you see here, it asked density of the air at standard conditions, water and seawater at 20 degrees centigrade and mercury at 20 degrees centigrade. So now the question is the material here, this is air, right? So this is air. We need to calculate the density of air at a standard condition. What do you mean by standard conditions? So for air, a standard condition is 20 degrees centigrade, right? And you can see for water and the seawater at 20 degree, and then for mercury this is 20 degrees centigrade. So that means we need to calculate the density of air, water, seawater and mercury at 20 degrees centigrade. So just keep in mind the density of air. So at a standard condition means for air this is 20 degrees centigrade. If it is called seawater, then it is different. Then I will discuss that on later. So let's solve this question here. I actually want to save time. I don't want to increase the video length. So the density of air. So you can see the density of air, the water, seawater, and mercury at 20 degrees centigrade. I just wrote here air standard condition is 20 degrees centigrade. So how you will get it? See, this is the table for the air at a standard atmospheric pressure at 20 degrees centigrade. The density is 1.204. So if this is the question now, if the question is at 15 degrees centigrade, so it should be 1.225. So this way, okay? So it could be different, and in some cases it may ask, okay, calculate the density of the air at 22 degrees centigrade. So then you need to do some interpolations. You can see for 20 and 25, so you need to use this 2 value, and then you will do some interpolations, then you will get the exact value, right? So just go back here. So for air it is, this kg per meter cube, And now water, seawater and mercury. For your convenience, I included every table here, so go back. So this is you see, this is for water. So this is for water. You can see for 20 degrees centigrade, this is the water density. Now, okay, this is for standard sea level conditions. This table, it is actually for mercury. You see, for 20 degrees centigrade, it is 13545, and this is seawater. At 20 degrees centigrade, what's the density? Is this is 1025. So you will get all values there. You can see this is for air, this is water, seawater, and mercury. So we have all the values here. So it was your first question. Actually, the density of air at this. So I believe this is very simple. Now the vapor pressure of water at 5, 20, 50, and 100 degrees centigrade. Viscosity of water. Surface tension of water. Okay, so now I will solve these three questions, because this is, you see, all of these properties is related to water. So the first one, this is the vapor pressure, this is the viscosity, and this is the surface tension, but for different temperature. So now let's solve that one. Alright, so what I say is, the question was, we need to calculate the vapor pressure. So look at the table here. So it should be for water here. So the vapor pressure, this is the physical properties of water. You can see density, this is the specific weight, this is surface tension, this is vapor pressure, and this is the viscosity, the kinematic and the dynamic viscosity. I will explain the difference between the kinematic and the dynamic viscosity later. But if you see here, the question we had, we need to calculate the vapor pressure for different temperatures like 5, 20, 50, and 100. So if we see this table here, this is 5, 20, 50, and 100, and you will get the corresponding vapor pressure here. Similarly, you will get the surface tension for any temperature here. So this is pretty straightforward. So now I think I need to spend less time here. So I'll just write it down here, the vapor pressure of different temperatures. So this is for 5 degrees centigrade, this is for 20, 50, and 100 degrees centigrade. So this is the corresponding vapor pressure, and you will see the unit is written here, Newton per meter square. Similarly, when you have to calculate the viscosity, so the viscosity you will get from here, like for 5, 20, and 50. This is the corresponding value you will get from the table. I think this is not that difficult. Similarly, when you need to calculate the surface tension, so for 5 and 60 degrees centigrade, it is the value here, and you see the unit here. I actually write it down at first, and then I'm putting the picture here, because if I try to write, it will take a long time, but this is very simple thing. So I'm not just writing here, but I'm using this solution, so it will save our time. It will so that should be easier for you, because sometimes it is really difficult to watch long videos, so it's not good, and this is not very complex thing, so I think it's okay. Right, so the next question is, we need to calculate the bulk modulus of water at 20 degrees centigrade. Then the pressure required to reduce the volume of water by 1%. So just keep in mind this amount here. I just am telling you should concentrate now the bulk modulus of water at 20 degrees centigrade, and the pressure required to reduce the volume of water by 1%. So you can see the volume is decreasing 1%, and the water is at 20 degrees centigrade, and what is the pressure required? So if you read this question, if I ask actually what is our requirement, should I calculate the bulk modulus? or should we calculate the pressure? That's the question here. Right, so the thing is, what I asked you earlier, actually, are you going to calculate the bulk modulus of the elasticity of the water or the pressure? Definitely this is the pressure. How much pressure we need to reduce the volume of water by 1%, because we know the bulk modulus of water at 20 degrees centigrade. This is some sort of constant value. If you see, we have some sort of table here. Let me show. This is the bulk modulus for different fluids. You see, this is for sea waters, this is the water. So we know the bulk modulus of water, this is constant, so we actually don't need to calculate that. We need to calculate how much pressure actually required to reduce the volume is 1%. So let's solve this problem now. From the definition, if you can remember, we know the bulk modulus is E equal delta P and delta V over V, right? So this is actually the the pressure, and this is the relative change of volume. If you can remember, we explained the theory for bulk modulus. There is no negative sign. Can you tell me why it is negative? Because in this problem, the volume is decreasing 1%. So that means this is the negative. It is decreasing. So that's why this is negative here. So now E equal delta P over delta V by V. The bulk modulus elasticity of water at 20 degrees centigrade is this 2.17 and 10 to the power 6 kPa. So that means we know this E. We need to calculate this delta P. So that means we know this. If we know this value, that means if we know this delta V over V, then we can easily get the pressure. What is this? The delta V over V is the volume of water, which is reduced 1%. So that means negative 1, and percentage means 1 over 100, that means negative 0.01. So now it is straightforward. This is negative 0.01, you just substitute this value here. This negative sign you can eliminate. And you know the elasticity is this. So now if we eliminate these two terms, then delta P, it will be this. So this is actually the pressure required to decrease the volume 1%, right? So I believe you got some clear understanding actually how to calculate this bulk modulus.